if we have a time harmonic current J, then we can write down the magnetic vector potential A due to that current like this. Mu naught over 4 pi integral over some volume V prime J of R prime e to the minus j k r minus r prime over r minus r prime. Now, I need to talk to you for a minute about what r and r prime actually are. Haha, r. So, r is the observation point. That's where do we want to know what the value of the radiated fields are. Where do we want to know this vector potential? R prime ranges over the source coordinates. And it only exists, and it only takes values where J exists and isn't 0. So graphically, this might look like this. We have some source distribution with some currents on it, J, and if this point is the origin, R prime will take on values within this region where J is. And then, if we want to know the field at some observation point, R, all of these different values of R prime will have contributions that add together to the total field at R. So we do this integral over all the possible values of R prime. Whoops, I forgot that dv there. And then the result will only be in terms of R, not R prime, because we will have incorporated all the possible values of R prime. So R prime is eliminated from this integral. And so for each different value of the observation point, technically we have to redo this integral. There are smart ways to do that though, because we just leave it as a variable and evaluate it at the end. So in general, that is the way that radiation works. You have many different contributions from many different infinitesimal current elements, all adding up at one observation point. And then we let our observation point range all around the source to get a picture of how this source's radiation looks in the whole world. But I talked about infinitesimal current elements. Let's sort of talk about that a little bit more. So the total radiation is made up of the contributions from all of these different infinitesimal current elements. But what is the contribution from just one infinitesimal current element? Can we figure that out? By the way, these are also called a hertzian dipole. The contribution from each of these infinitesimal current elements. So we got to set up that radiation integral to find it. But let's draw a picture of what we're talking about. Here's our coordinate system. Let that be the z-axis there. And we're going to assume that we have a very short element of constant current and that's the total current, I naught, and it has cross-sectional area S. So our volume current density, J, is going to be Z hat I naught over S for Z within the range minus L over 2 to L over 2. So its total length is L. And now here's the thing. This is an infinitesimal current element, so L is very small. And S is very small. And we've said that the current is constant on this current element. Otherwise, it's not really useful as a building block for integration. If we set up our radiation integral under those constraints, we got mu naught over 4 pi, just like we normally would. We got the integral from minus L over 2 to L over 2. Now, since our current is constant over the cross-sectional area, dV here, or dV prime, just has to be S dZ prime. Then we've got Z hat I naught over S e to the minus j k r minus Z hat Z prime over magnitude R minus Z hat Z prime S dZ prime. And now here's the thing. We just said L is very small. How small is it? L is so small that this term is constant. Over its length. That's what infinitesimal means. So if that is the simplification we can make, then we've got that the magnetic vector potential due to this hertzian dipole is mu naught over 4 pi. This Z hat just moves out to the front. I naught over S times S, so that S's cancel. We integrate I naught dZ from minus L over 2 to L over 2, so we got I naught L. And then we got e to the minus jkr over r. That's the magnetic vector potential due to a hertzian dipole. And this, like all other radiation integrals, the result is only in the unprimed coordinates r. Now that we have the magnetic vector potential, we can find the magnetic and electric fields due to this dipole. I'm going to write down the equations for finding them, but I'm not going to write them all the way out because those are in the handout and I don't want to spend a lot of time for you to have to listen to me do it. So we can find that the magnetic field due to this dipole is 1 over mu naught times the curl of A. And the electric field due to this dipole, or really due to anything that has a magnetic vector potential, is 1 over j omega epsilon naught curl of H. So that lets us find the fields for this dipole. from its magnetic vector potential. Nice. Now what I want to point out here is that this vector potential has this e to the minus jkr over r term in it. And that term is also going to show up in the electric and magnetic fields for the dipole. That term is very important and special, and it has a special name. It is called the spherical propagation factor. And it shows up in all fields from finite sources. In this particular form, we have to say that it's time harmonic. But there's a similar thing that shows up in time domain sources too, so you don't get away from it ever. So we've got e to the, let's look at it, e to the minus j k r over r. This 1 over r term is going to describe the amplitudes decaying as you move away from the source. And this e to the minus jkr looks like the phase propagation factor from a plane wave, except this one doesn't have planar phase fronts. It has planar phase fronts that are surfaces of constant r. A surface of constant r is otherwise known as a sphere.